So hello everybody, my name is Martin Monperrus. I'm professor of software technology at KTH Royal Institute of Technology in Sweden, in Stockholm, wonderful city. And I'm here today to talk about a fight, a long-standing fight, a fight between bugs on the one hand, and on the other hand, plenty of researchers, practitioners, trying to eradicate them, literally. So there have been lots of research about detecting bugs, which is one part of the fight. Huge amount of research about proving the absence of bugs. Like, I don't want them in my world. But you know, if you look at data from last year, for instance, so last year there was something like 12 million of bug reports on GitHub, which is an underestimation of the total number of bugs in the world. So which means that basically the fight has been completely lost, so at least with traditional techniques. So there is something wrong here. We must take the problem in another way. And this has been done first at the end of the years 2000 in a very seminal paper by the University of Virginia in America, where they say, okay, well, we have bugs. They are here. There are plenty of them. So let's try to automatically repair them. So because it's easy to detect, so many people detect bugs every day. It's super hard to get rid of them. But maybe we can try to repair them. And it was a fundamentally new idea. Basically, you can find some traces in the literature before, but there was virtually nothing. So nobody before that paper has ever thought of taking a bug and trying to automatically repair it. So what does it mean, repair? It means writing a patch, a piece of code, a small change, maybe a small patch, maybe a one-liner change in the code base, and try to repair it. And that paper, it's fundamental for the community. It was fundamental for me, you know. When I read this paper, I said, wow, that's mind-blowing. It's just completely different way of putting things. It's crazy, but maybe it can work. And maybe, 12 million of bugs, even if we can repair them, 1% of them automatically, this can represent a huge amount of human effort, which means a huge amount of money, basically. So there is something, even a small success, like 1% of automatically repaired bugs would be something very significant for the software technology world. So this has started, and a number of researchers came in, including myself, my students, and then we came to the second part of this talk, achievements. So, number of research projects, talented PhD students coming in, and we invented in different groups, different automatic repair systems, such as Nopal. So what is Nopal? It's an automatic repair system. It takes as input some Java source code. It takes as input one bug in this source code, test cases. So, a typical Java project, you can have like 1,000 test cases. And so you assume that among those 1,000 test cases, you have one failing test case. So with this failing test case, it shows that for some input, the behavior of the program is incorrect. And you also have 999 99 passing test cases. For the rest of those test cases, it works. So what the goal of NoPoll is to find a change in the program such that the failing test case passes, which means that the bug has been fixed. But we also want all the other test cases to still pass. Otherwise, we would have introduced a regression. And any practitioner knows that it's very easy to break something in the system, in a software system, without noticing it. So it's the same thing when you put a program repairing another program, it's very easy to break it, basically. So yeah, that's the problem statement. One failing test case, 900 passing test case, find a change such that all test case passes. And then we can think, okay, so we have a problem statement, what's the search space? So the search space, basically, it's all possible edits that can be made to the program. So 1 character edit, 2 characters edit, 1 token, 2 tokens, 3 lines, 70 lines, I don't know. So it's infinite, so there is an infinite search space. And so the whole point of this research is that in this virtually infinite search space to define a sub-search space which is tractable. And so one way of defining a tractable search space, and that we have in NoPoll, is that, okay, let's assume that we won't be able to repair all bugs in the world. So only some of them. So let's assume that we will target only one specific type of bug, which is common in practice, which is a bug in an if condition. So in source code, I have if A equals 1, do something. And you know, maybe the bug is that it should be if A equals 2, do something. This is a patch, and you can find such patches in any large software system. So one way of analyzing the problem is that, okay, I have a bug somewhere in an if condition. My failing test case executes, let's say, 10 if conditions, which is a very low figure compared to reality. What I can do is that when I execute the failing test case and comes to one if condition, instead of evaluating the actual condition, I can force it to be true or force it to be false. It's like, you know, I want to go to my grandmother's house, and I don't know exactly the way, and at some point the GPS tells me, turn right. I turn right, I continue the execution, and if I arrive at my grandmother's house, it means that turning right was the right choice. So which means that if I take an if condition, if true, and I resume the execution, and at the very end, the test case passes, it means that it was actually the right solution. So the thing that has to be, the correct thing was to return true for this if condition. So now I have made half of the path to the repair, and the other half is to find a Boolean expression which returns true. So this is one technique among others. So there are plenty of very clever techniques in the literature for program repair, and it works. So for some real bugs, so to evaluate such systems, what we do is that we take open source software, we take real bugs reported in open source software, and we run the system. And we see whether the system is able to find a patch which is the same as a human patch. And so today, I would say that more than 100 bugs have been fixed by such systems, either this one or others, of real open source software. No, it's not that easy. Because at the beginning, back in 2009 and 10, everybody thought, this is super hard, so the search space is infinite. But if you come to find one patch, super cool, it must be the good one. And then people started to experiment, so we did a lot of experiments as well. And we realized that actually, for many bugs, the problem is not to find one patch. For many bugs, there exists a lot of patches such that all tests pass. When I mean a lot, it can be 5, it can be 10, it can be more than 1,000. So this was a huge surprise for all researchers in that field, where, okay, so the problem is not to find one patch, the problem is to select the good patch among a huge amount of patches. And this is a hot topic today, well, how to find the good patch in a huge amount of patches. Now, let's come to the end of this talk and to try to talk about the future. This is super recent work that will be presented next month in Göteborg. It's about Repairnator. So we had a lot of movies in the previous talk. Terminator, you know that American blockbuster, kind of dystopic actually. Repairnator, it's positive, it's having a robot helping you to fix bugs. This is a vision of Repairnator. So the idea here is that, again, so if having bugs, we have millions of them, and having failing tests, we also have millions of them in something called continuous integration. So the idea of continuous integration is to run all tests for any change to the code base. And any serious software project uses continuous integration. And so basically, so for instance, one of the most successful companies in that area is called Travis. The headquarters are in Berlin. And Travis, they run 1 million builds per day. 1 million builds per day. And so in these 1 million builds, many of them fail. Okay. And so what Repairnator does is that, okay, it looks at a build failure and tries to repair the patch before the human. So this is where Program Repair is human competitive as art, because what we try to do is to have a robot repairing a bug instead of a human. Before. So it's been running for a year now, more than a year, and we have had some success, such as like back January 12 this year, at small story to end. So at noon, a developer called Andrea Eimer, I don't know him, he's working on a project called GeoWeb Cache. And so he pushed a commit at 12:28. The commit failed, so there was a build failure. And 30 minutes later, a Repairnator came and wow, there is a build failure. Repairnator executed the repair system and sent an email to us, the Repairnator team, 10 minutes later, so at 1:18 p.m. At 1:35, one of us in the team opened the email and said, wow, that looks like a human competitive patch. It was quite good. Let's submit it. So it was submitted at 2:10 p.m. And 5 minutes later, the change which was proposed as a pull request on GitHub was merged by Andrea, and Andrea replied, oh, weird. I thought I already fixed this, or maybe I did it in some other place. Thanks for the patch. And so here, Andrea, as a human developer, accepted a patch made by a robot and presented with a fake human identity, which is one step towards human competitive program repair. So as a conclusion, automatic repair is a new mindset, less than 15 years, where the whole point is to get a search space tractable, because otherwise it's just infinite, it's crazy. There is a major challenge of finding the good patches in all possible patches. And finally, we are now inventing a future where there will be human developers and bots cooperating on the same code base. And this is what we are doing at KTH. Thank you very much.